So today, our first speaker is Dr. Alexandra Veledina. So she received her PhD degree from the University of Oulu, Finland in 2014. The work was awarded Vasala Prize for the Outstanding Astronomy PhD thesis, and in the Finland over 2014 to 2015. After the PhD, she moved to for Nordita fellowship position in the Stockholm, Sweden, and after that shifted to a Nordic assistant professor position in a joint appointment between Nordita and the University of Turku in Finland. During the same period, she served as an Academy of Finland postdoctoral researcher employee. From 2022, she joined the staff of the Department of Physics and Astronomy at the University of Turku. Her interests concern processing in the vicinity of compact objects. She has mostly worked with accreting black holes. Her expertise includes fields of radiative process, timing analysis, and multi-wavelength optical and X-ray, for example, polarimetry. She is a member of several instrumental collaborations, including XP from 2019. So today, Dr. Veledina will give us a talk about the puzzling microquasar Cyg X-3 observed in polarized X-ray light. The floor is yours.
Thank you very much. So I'll start the first piece of today's puzzle, the puzzling accreting black hole, the microquasar Cygnus X-3, observed with the X-ray instrument, which was launched a little bit more than a year ago. XP, so imaging X-ray time, X-ray imaging X-ray polarimetry explorer. Yes, now I got it correct. First of all, I would like to say a few words about the system. So the system has been discovered in the early X-ray era in 1966. This is the third in brightness. This is the third source in the constellation of Cygnus, but it is also variable, and it sometimes exceeds in brightness the Cygnus X-2 and can in fact sometimes be more bright than Cygnus X-1. So the source has high interstellar medium absorption, so there is no optical counterpart visible. It is located close to the galactic plane. However, it shows infrared, it has an infrared counterpart. It shows also variability in the infrared. In particular, it shows orbital variability, so the star, the compact object in the binary orbit with the companion star. And the distance to the source is about 7 kiloparsecs. It shows prominent X-ray orbital modulations with the period of about 4.8 hours. Also, in the infrared, the same modulation with the same periods have been observed. So, and this is rather atypical for the high mass X-ray binary. So when the companion star in the X-ray in this binary is known to be the Wolf-Rayet star. So this is the high mass X-ray binary, and it possesses a quite short orbital period. So the source is also exceptional in terms of the gamma rays. It is one of a few gamma ray sources, galactic X-ray binaries with gamma ray detections. And this is the only source which we have in our galaxy with the compact object in the binary orbit with the Wolf-Rayet companion. So this is a progenitor for the double degenerate system, maybe either neutron star or black hole neutron star system in the future. So here I show the orbital X-ray light curves. They're rather prominent, and another interesting property which the source shows is the very bright radio emission. So this is the source is among the brightest radio sources on the sky, and detected fluxes can be as high as 20 Jansky, which is very atypical for the accreting black holes. So for typical accreting black holes in our galaxy, we measure the fluxes of around maybe 0.1 Jansky, so like 100 millijanskys. And for this source, the orientation of the radio emission has been detected. It is roughly in the north-south direction. So the radio comes from the extended jet in the source. And in different wavelengths and different times, this jet has been detected. Now, another property, the source has been studied quite extensively. It possesses many interesting details, and orbital inclination for this particular source has been measured using different methods. One of that is the Doppler shifts of the X-ray and infrared lines. From that, so one is corresponding, so the Doppler shifts of the infrared lines would correspond to the companion star, to the Wolf-Rayet star, and then for the X-ray lines, you can also infer the Doppler shifts, and that would be somewhat associated with the compact object. And from these two estimates for the mass functions, you can determine the inclination of the system, which would somewhat depend, of course, on the mass of the companion of the Wolf-Rayet star. Another estimate comes from the one-side Doppler boosted approaching jet, which has been detected in the system. So, for instance, here in the picture, it was detected as and interpreted as a one-sided jet. Then you can also infer the inclination with respect to the jet. On the other hand, for the two-sided ejections, the estimate again can be made, and it is also consistent. So the inclination of the binary is rather low. So the latest estimates come from the simultaneous fit of the infrared and X-ray photometric orbital variability, and basically the orbital profiles which are coming from the absorption along the line of sight. The estimate would give, again, consistently low, around 30 degrees inclination to the source. So this is going to be important. The inclination is going to be important for the subsequent discussion. Well, I mean, the evolution of the source through different X-ray states is shown here. So the source is variable in the X-ray sky. It is variable in terms of the spectrum. So sometimes it shows the hard spectrum, and then it switches to the ultra soft spectrum, which are shown here. Together with that, also the radio properties change. So the source, as the source softens, the radio flux goes through this rather difficult loop. So it first increases, then decreases to very low fluxes, and then goes up to a very high, bright flaring events. So the changes are somewhat connected to the accretion geometry of the source, but it was not clear for a long time how exactly you can reproduce this kind of behavior. So if we compare for the typical X-ray binaries, there is a general trend of the radio X-ray correlation, but there is nothing like this kind of weird behavior with the hook here. Another complication to the source is the uncertainty in spectral modeling because of the high absorption along the line of sight also, within the binary there. The source can be, the hard state, for example, the hard spectrum of the source can be explained with different geometries with different spectral components. So here are three examples. First of all, so here are the data points in the color. This is the fitted spectrum, and this is the intrinsic spectrum in the source. So this spectrum corresponds to the soft initial spectrum, which is severely absorbed in the Wolf-Rayet wind. The same spectrum can be fit with the standard hard state spectrum similar to other accreting black holes, but then with some contribution of the non-thermal electrons here above the cutoff. Or it can also be explained with the spectrum where you have a high contribution of the reflection features. So it is always compared to another prototypical X-ray binary Cygnus X1, but it is not quite the same in terms of the spectra. Because of this, exactly 50 years ago, there was a paper appeared in Science, which was called an astronomical puzzle called Cygnus X-3, and which described in details how puzzling the sources, how difficult it was to understand it at initial stages what happens in the source, because it was not performing the same way as people would have thought, and it actually continues to surprise us over the years. Now we tried to, or we actually observed the source with the XP satellite, which is sensitive to the polarization of X-ray radiation. So the polarization is the property of light that where you have an excess of photons with electric vector oscillating in certain direction. So it's not only random in the plane of the sky, but it has a preferential direction. And using this property, it is possible to extract or to determine the geometry of the system. So the source was observed with XP twice during the October observation, which is going to be called the main observation. It consisted of 2 runs in mid-October and beginning of November, and then another time shortly after the source started to transit to the softer states, which we call the TO observation. It was performed around the Christmas time. There were simultaneous new star observations. Here is the picture showing 2 spectra, the blue for the main observation and the orange for the TO. So the spectrum has changed quite a lot, especially in the XP range, so between the 2 and 8 eV. So here is the average polarization degree, which has been detected in the source. This is plotted in the QU plane, so the Stokes parameters. And basically here from the origin, the length of the, to the point, the length of the vector to the point gives you the polarization degree, and the position angle in this graph would give you the position angle on the sky, the polarization angle on the sky. And here 0 would correspond to the north-south direction, but what we detect is that the polarization is orthogonal to the north-south direction. It is directed in the east-west, and it is perpendicular to the, or orthogonal to the jet direction, which we see in the system. So the 2 observations, the main and TO, give consistent average polarization angles, but the polarization degree has dropped by a factor of 2. First of all, I mean, what I wanted to emphasize here is that the polarization degree is exceptionally high, so something that we expect typically for X-ray binaries for the, for accreting geometry is in the range between maybe 1 and a few %. What we detect here is over 20%. How to produce the polarization? There are 2 basic processes which could be relevant to the system. The polarization can arise from scattering. If your initial photon travels and scatters from the electron here, the initial photon beam can have any direction of the electromagnetic radiation, so not one photon, but many photons, so there's all the directions are equally probable. But then after the scattering, you are reducing the component of the electric vector, which is going to be along the direction of the scattered photon. So in the case, for example, if you have almost zero angle scattering, you preserve all the directions. But if, for example, you are scattering at 90 degrees, the only polarization, the only photons which can be scattered at the 90 degrees angle would have the electric vector, which is orthogonal to the propagation of this of the scattered photon. So the polarization is going to be orthogonal to the scattering plane which you have in the system. Another possible scenario is the synchrotron radiation. In this case, you have if you have a structured magnetic field, then your electrons will be moving around it, and then they will emit radiation in certain direction with the polarization which is orthogonal to the direction, of course, of the photon, but also orthogonal to the magnetic field. Both the GR and SR effects may modify the polarization produced in the local frame. So to understand what is the main production mechanism in this case, in our case for the Cyg X-3, we considered the energy dependence of the polarization. Here for the main, this is the polarization degree as a function of energy and the polarization angle as a function of energy. So we see that there is no dependence of the polarization angle on energy, and there is nearly a constant polarization degree both for the main and for the TO observation. For the main, the only drop which we see, or the only difference which we see, is around the iron line, the prominent iron line which we see here, and it basically gives you depolarizes you the total signal. But if we consider, for example, the energy range between 3.5, and 6 keV, the polarization degree is nearly constant. So another interesting finding is the orbital dependence of the polarization degree. So this is also something that can give you a clue of what scatters from what in the system. So we studied the orbital variability, and we folded the polarization signal with the orbital period. Here it is shown for the QU plane in terms of the for different phases. So here is the phase 0, and what the polarization does, it makes one loop in the QU plane here. And the similar thing happens in the TO observation. Here is just the same thing, but plotted as a function of the orbital phase for the polarization degree and the polarization angle for one orbit. So there's one loop the polarization does for the orbit. So immediately from this topology, we can say that this scattering does not proceed, for example, on the surface of the companion star, just because in this case, what we expect to have is the two loops, so the two peaks per one orbital period. Just because if you have a scattering from the companion star, whether it's scattering from in the first quadrature or the last quadrature, it doesn't matter. So you have the same polarization signal. So in one cycle, you will have two double sine wave for the polarization. So this is not something that we observe here. Another clue that this is not really coming from the scattering of the companion comes from the fact that we have a high polarization degree. If we correct for the contribution of the fluorescent iron line, which is non-polarized, the total polarization degree that we see is around 25%. So the fact that the polarization is orthogonal to the jet, that the polarization, that we have high polarization degree, and indicates both that we do not see the primary X-ray source at all. What we can see is just the scattered or reflected, in this case, light from some matter which obscures the primary X-ray source. Another clue here that the scattering comes from the that the polarization comes from the scattering comes from the energy dependence of the polarization. To make a nearly energy independent polarization, you need to have one scattering event. So it's a single scattering, because if you have a subsequent scatterings, then your polarization is going to be energy dependent for different scattering orders. So what we propose as the geometry for the system is that if we don't see the primary X-ray source for the observer located at inclination of around 30 degrees, it means that you need to have matter, obscuring matter, high up above the orbital plane. And we propose that this matter forms this kind of a funnel. So a way to put your matter up above the orbital plane is to make the super Eddington accretion. So then in this case, you will have a lot of matter would rise above the accretion plane. So here is the plot for the inclination and the opening angle of this funnel. So alpha here and the inclination of the observer here, and the counter plots would give the polarization degree in percent. So what we expect to have at around 30 degrees, we can have either 25% either for the opening angles nearly the same as the inclination of the observer. So we are looking right along the funnel, down the funnel, or we can have a narrow funnel and the reflection from this kind of funnel walls, which are then going, the photons would then go into the observer. So for this branch, we do not think that it is feasible, just because there is a small, if we have a small changes in the opening angle of the funnel, there is a huge change in the polarization properties, which we do not observe. So the polarization is rather stable with the orbital period and with time, basically, between the orbital periods. So we think that we are somewhere here in this branch. We did the same thing with the Monte Carlo simulation. So here, what I showed is the analytical calculations of the single scattering events in this geometry, and then we can do the same using the Monte Carlo simulations with slightly different geometry to show that this is not really like the results is not really geometry dependent, as long as we have the obscuration medium. So this is the same plot, but with the Monte Carlo simulations, which were done with this cold stocks. And then we see for the same polarization with the 25 degrees, we see very similar contours and very similar values for the alpha, which just basically shows that the analytical estimates can be applied in this case. So what we find is that this primary X-ray source is surrounded by a very narrow funnel here with the opening angle of between around maybe 8 and 15 degrees. So what then we can do with this funnel, if you have the source which is covered by the funnel, you can estimate the total luminosity which an observer looking down the funnel would see. And what we estimate here, we assume that the primary source, X-ray source, is more or less isotropic. So the luminosity you get in certain solid angle is proportional to the solid angle. And what we see is just the reflection of the funnel walls. So using these two solid angles, we infer the luminosity in the direction along the funnel, and we obtain that it should be over 5 × 10⁻39 ergs per second, so it exceeds the Eddington limit. Another point here is to say that we need to have the super Eddington accretion, then we need to have the bolometric luminosity, which is also exceeding the Eddington limit. For this, we of course need to make a little bit more modeling. For example, what we need to assume is the bolometric correction for the flux. So we did these estimates, and what we obtain is that depending on the funnel opening angle, we can obtain between 5 × 10⁻38 to 5 × 10⁻39 ergs per second. So we are going to get super Eddington accretion either for the neutron star or for the black hole. So as my conclusions, the first polarimetric observations of the galactic X-ray binary Cygnus X-3 shows that the X-ray emission is highly polarized in the direction orthogonal to the radio ejections. Both the spectral properties, the independence of the polarization of the energy, suggest that the polarization arises from the single scattering event, and which we interpret in the context of the optically thick outflow scenario, so that you have a narrow funnel and then you only see the emission which is reflected from the walls of the funnel. So both our estimates of intrinsic source luminosity and the apparent luminosity in the direction of the funnel show that the source exceeds the Eddington limit, and that it means that we find for the first time that the Cygnus X-3 is well, one of the most intensively studied sources in the X-ray sky is an obscured galactic ULX. That's all from my side. Thanks for your attention.
Thank you. Questions? So while people are thinking, maybe I can ask a very naive question. So I always see the UV plane on this kind of polarization figure. So could you comment more? What's this U and Q?
So these are two Stokes parameters which basically determine the orientation of your polarization. So for example, these two Stokes parameters can be related to the polarization degree and the polarization angle. So what you have, for example, for the Q or Stokes positive Q, it means that your polarization is going to be in the in the north-south direction if you measure from the angles, your angles from the north. So it means basically that your oscillations, predominant oscillations, are in this direction. Then for the negative Q parameter, your oscillations are going to be orthogonal to that. So the same thing you can think in terms of the polarization angle. So what would be the relevant angle at which you see these oscillations? So the two, basically these two sets are equally possible to use, albeit the Stokes parameters would, like basically the Stokes parameters would give you the vector, so you can operate with these parameters as with the vector, while the polarization degree and the polarization angle, the polarization is in fact the pseudo vector, so it doesn't have a direction, it has only the the orientation of oscillations.
So that's why you think the emission we see is from the reflection of the outflow rather than the jet.
So basically what this picture tells you is that your oscillations are orthogonal to the jet. So it's not, so you have this, the jet is north-south, and then your oscillations are going to be orthogonal to that. So it means also, it also shows you where your scattering plane is, because your scattering plane has to be orthogonal to the orientation of these oscillations. So
Thanks.
for the jet, there is another, there was some question about the jet, basically why it's not the jet. Well, for this particular observation, we have a simultaneous SMA observations, SMA, with the polarization, which is rather, I mean, the significance is not very high, but in principle, the polarization angle there is consistent with the north-south direction. So it's totally orthogonal to what we see in the X-rays. That is one of the reasons why we think it's not coming directly from the jet, for instance.
Thank you. So Anita, I saw you have a raised hand, please.
Yes. Thank you for very good talk. This is amazing, actually, these results, and seeing the results which confirm the scattering as a main source of polarization. So I'm wondering if, you know, how bright is your source and whether or not we could observe the extragalactic source, the galaxy, which we know is covered by obscuring medium. If it's possible to observe such a source and look at the polarization in X-rays. I mean, I don't know what's the, you know, flux, X-ray flux of Cygnus X-3.
Yeah, I mean, so here I don't have an obscured flux. This is some units times 10 to minus 9. Well, it's like,
oh, 10 to minus
like
9. Okay, that's pretty high.
Yeah.
Okay.
Yeah, this is one of the brightest sources.
Yeah,
but like concerning your question about the galaxies, so for example, XP collaboration had a paper about the Circinus galaxy, where we observed 28% polarization.
Oh, wow.
And
yeah.
that was, but that was at a higher inclination, like more than 60 degrees. So you are able to get this kind of polarization. You are somewhere here.
Right.
Amazing thing about the Cygnus X-3 is that the polarization is around the same, but the inclination of the source is really low.
Yeah.
So that's something really, we think, really unique.
Yeah, Circinus is really the obscured galaxy. The central AGN is obscured by thick matter. So nice, thank you. That was very nice. Thanks.
Thank you very much.
We have further questions? If not, we can go to the next speaker.
Thank you, Alexandra. Okay, Mehr, can you share the screen? Perfect, thanks. While you do that, let me introduce you. So we have the pleasure of the second speaker, Mehr Nisa. She's an experimentalist working on neutrino and gamma ray astronomy. She grew up in Pakistan and got an undergraduate degree at LUMS. Then a PhD at University of Rochester in 2019, working on the Hawke Observatory and direct detection of dark matter. She's currently a postdoc at the Michigan State University, where she splits the time between IceCube and Hawke, searching for the origin of the cosmic rays in the galaxy. And today she's going to talk about another puzzling problem, which is the puzzling sun in the very high energy gamma rays. And with that, Mehr, the floor is yours. Thank you.
Thank you. Yeah, I hope you can hear me all right. Yeah, so compared to Cygnus S3, I'm going to talk about a puzzle much closer to home, and that's about our very own sun. So, okay. So, as we know, just by virtue of its proximity, the sun has been studied to death in nearly every messenger possible, at least at low energies. It's, in fact, the only astrophysical object from which charged particles can reach us without their directions being completely smeared out. And it has a history of teaching us about fundamental physics, for example, solar neutrinos. So this is an image of the sun taken by the Super K experiment, which is reminding us that the sun had a key role in teaching us about neutrino oscillations, for instance. But these are at somewhat low energies, about a kilo-electron volt. And today I want to focus on non-thermal processes in our sun at much higher energies, at GeV and TeV. So, and that leads us to the question of cosmic rays. these really energetic charged particles. They could be created in particle accelerators like supernova remnant or in some unknown beyond the standard model processes. And they also have to traverse close to the sun before they reach our detectors here on Earth. And these cosmic rays have to grapple with a very dynamic solar environment. The sun has a very vibrant and complicated magnetic field of its own, and the highest energy cosmic rays are able to penetrate this. And we care about what happens to these extremely high energy particles as they pass close to the sun. And we have been studying cosmic rays that survive the sun's environment and reach us here on Earth for decades. And when I say Earth, I mean both ground-based and space-based detectors. And there have been observations that reveal a clear modulation of the cosmic ray flux with the solar cycle. And these cosmic rays form the background to almost every particle physics experiment that you do on Earth, especially if it's not buried deep underground. And I will come to gamma ray astronomy shortly, where we have kilohertz of cosmic ray showers we have to deal with all the time. And that's all the cosmic rays that survive their passage close to the sun before reaching us. The question we're talking about today is what about those cosmic rays that don't survive and instead crash straight into the sun? And these cosmic rays are thought to be the reason the sun glows in gamma rays. So, and these gamma rays come in three distinct components that you can see here. One would be this diffuse halo around the sun, which is produced by high energy cosmic ray electrons upscattering by solar photons. So that's why it's also sometimes called the inverse Compton halo around the sun. And what has so far been observed of this halo matches what you expect based on the cosmic ray spectrum. Another possible component is this ring around the sun, also known as the solar limb, which is basically the outermost limb layer of the sun. So how would we get this limb emission? So imagine what happens when TeV cosmic rays bump into the sun. They would encounter a column density of hundreds of grams per centimeter square, and they would die or be absorbed straight away. Their only chance of survival is in the outermost layer of the sun. That is, if they just graze the surface of the sun, producing gamma rays via pion decay, and that can escape without being absorbed. So that will be a very tiny fraction, but if it's happening from all directions, you would expect a very bright ring of gamma rays with a completely dark disk in the middle. So we don't observe this limb currently because no gamma ray instrument has the angular resolution to resolve a thin ring around the sun. And also the predicted flux is way below the sensitivity of current gamma ray telescopes like Fermi. The gamma ray component of the sun that we do observe and found the most interesting sort of surprises is the solar disk itself. And I just told you that any cosmic rays crashing into the solar disk will die. So how do we get this gamma ray flux? Well, the only way you're going to get photons from the disk is that if these cosmic rays are somehow reflected within the solar atmosphere, and this outgoing component produces photons. So remember, the sun also has a magnetic field structure of its own, and that will cause some of the cosmic rays to be mirrored in the sun's atmosphere. And in this process, a cosmic ray proton would have its direction reversed by the magnetic field. And on its way out, it will interact with the sun's atmosphere, producing pions, which would then decay to produce gamma rays and neutrinos. Okay. So, but this process of cosmic ray mirroring has to be very finely tuned. And the most sort of rigorous calculation comes from this 1991 paper from Cyg, Stanel, and Geiser, and in which they predicted a detectable flux of gamma rays in the future. And the mirroring sites would be these so-called flux tubes on the surface of the sun, where the magnetic field can reach above 1,000 Gauss. So what you expect is the primary cosmic ray coming in, it's going to turn around and produce gammas. But note that even in this mechanism, you would expect a break when the primary is just too high energy to be trapped or mirrored by the field of the sun. So as far as the theory goes, this is more or less what we know about the cosmic ray interactions in the sun. A lot of details we actually don't know, which brings me to the question, what about the observations? So here's a plot of what has been detected from the sun in the first 9 years of the Fermi Gamma Ray Space Telescope. And these have been detected up to an energy of almost 200 GeV. And there are a few surprises in the data. So it was found that the observed flux is almost a factor of 7 higher than the predictions. The two observational bands that you're looking at here are from 2 different time periods. The blue one is solar maximum and the red one is solar minimum. So you can clearly see that the solar minimum flux is much higher and harder than the solar maximum flux. And it looks like it will continue to much higher energies. This black line that you see is called the cosmic ray upper bound. This is basically a very simple calculation of telling us what's the maximum gamma ray emission we expect from the sun, assuming that every single cosmic ray that is hitting the sun is being turned around with 100% efficiency in producing gamma rays. So you can see that already the observation is pretty close to this upper bound. So what is going on essentially? One way of answering this question would be, to come up with better models of what we know about the sun. And other possible routes that you can take as an observer is actually try to look at the sun at even higher energies, including TeV energies, and see if the spectrum continues or if cuts off, or whether we can get some upper limits or even observations, because that can give us clues about, what is going on with the sun. The origin of this dip is also unknown, by the way. We don't quite understand why the flux suddenly falls around 40 GeV. Okay, so yeah, this is the question we started with, that whether we can observe the sun at TeV energies. So, we cannot do TeV observations of the sun with Fermi. So TeV gamma ray astronomy is basically entirely ground-based. And there are observatories on almost every continent now, and they fall under 2 distinct categories. One is what we called ISETs, or Imaging Air Cherenkov telescopes. In some sense, they are very similar to traditional optical telescopes, excellent angular and energy resolution. The downside is they only operate at night, which means we cannot observe the sun. The way around is basically using these large arrays of telescopes at high altitudes. And, with these wide angle surveys, we can observe the sun because they operate 24/7 and don't have that limitation. So the observatory that I'm going to be talking about today is HAWK, that has been taking data since 2015. And I'll tell you about our HAWK observations of the sun. Okay, so HAWK is basically, stands for High Altitude Water Cherenkov Observatory. It's located in Mexico, near Puebla, between these 2 volcanic peaks. If I zoom in, you're looking at an array of 300 steel water tanks, and each tank contains 200,000 liters of purified water with photomultiplier tubes at the bottom. So a charged particle produced as a result of a gamma ray or cosmic ray shower will come in, pass through water, produce Cherenkov radiation, which is then registered by these photosensors. And the observatory covers an area of 22,000 meters square. And basically, since it's not a pointed telescope, its field of view is basically the entire overhead sky. And for energies above 10 TeV, it is among the most sensitive instruments that we have today. Okay, so let's come to the main observational challenge of looking at the sun from ground up. And that's the problem of what we call the cosmic ray shadow. So the shadow refers to the fact that cosmic rays are actually blocked by the sun, which results in fewer cosmic rays arriving from the sun's direction. So we actually observe a deficit of a few percent in our data. And this is basically the major challenge for ground-based observatories. And the bulk of data analysis is actually devoted to coming up with creative ways to minimize this, improve how well we're able to separate gamma rays from cosmic rays and, getting our simulations right. So basically, this shadow introduces a big hole in our background. Okay, and not only is there a deficit, the cosmic ray shadow also depends or changes with time. So here is what the roughly 10 TeV cosmic ray shadow looks like in Hawk data. This black cross marks the position of the sun, and the color scheme is such that red represents higher number of cosmic rays, and yellow to blue signifies fewer cosmic rays. So you can clearly see that not only is there a deficit at the position of the sun, it also changes, depending on what time we look at our data. And the shadow gets deeper and deeper from 2015 to 2020. And this is a clear variation with the solar cycle. So just a reminder about the solar cycle, we've been taking data since 2015. And today I'm going to be showing you results up to middle of 2021. And in terms of solar cycle, the first few years of Hawk, that's when the sun was more active. It was just coming out of the solar maximum. And recently, 2018 onwards, we've been in the solar minimum. And now the sun is going back towards higher activity. Okay, so I told you that the sun not only changes with the sun shadow, not only changes with time, but also it also has a dependence on energy. For example, this is what a cosmic ray shadow would look like at the lowest of our energies, just below a TeV. As I go to higher energies, you can see it's deepening. The deficit increases because cosmic rays are less and less affected by the sun's magnetic field. So at about 50 TeV, we can take data up to hundreds of TeV, and the cosmic ray becomes more and more deeper at higher energies. Okay, so what does this have to do with trying to take data, gamma ray data from the sun? I told you that the sun shadow is actually a challenge. What I mean by that is that it's a problem for us because we're after an excess of events from the solar disk instead of deficit. So think about making any experimental measurement where you have some background and you're trying to look for an excess or bump above your background. What actually happens is that there is a shadow, and that actually ends up eating part of your signal. So, you can imagine a crowded region of the sky hosting multiple sources, if you're doing an astrophysical measurements. But if one of your sources is negative, it ends up eating the flux of its neighbors too. And that is exactly what this shadow does to our signal as well. So fortunately, this negative source in this case is entirely made up of protons or hadrons, because the sun shadow is only produced by cosmic ray protons. And if we know its shape and its intensity, we can subtract it from our data to reveal any underlying gamma ray sources. And this is exactly what we do. So here's the method that we use. We measure the shadow in our data without applying any hadron cuts. So basically 99.9% of our raw data is in fact cosmic ray protons or hadrons. And then we repeat the measurement after applying cosmic ray cuts or hadron cuts that get rid of these protons. So that would in turn weaken the shadow, and then we can subtract and compare the two to see what residual is left, and that is interpreted as gamma rays. So here's, for example, a schematic picture of the method. So in the absence of gamma rays, what you're looking at here is basically data as a function of angular distance from the sun. So, before any cuts, you see that there are fewer counts close to the sun than away from it. So this is what represents the shadow. And in the absence of any gamma rays from the sun, once you apply the method, you will basically be left with no residuals. On the other hand, if there is a gamma ray signal from the sun and you subtract the shadow correctly, you're left with a residual which is coming from the gamma ray excess of the sun. So this is exactly what we do. So, we measure the cosmic ray shadow as best as we can, and I showed you the shadow at various energies and also times. And here is the 2D profile on the left and the 1D profile on the right. And you can clearly see there's a deficit with respect to the background close to the sun. And as you go away from it, it approaches your background measurement. So this is 6 years of Hawk data at roughly 1 TeV. Then after we apply hadron rejection cuts, we've gotten rid of more than 80% of our cosmic rays in this particular bin. And that is why the shadow now looks much weaker than what it was earlier. And once we, scale the two and subtract, we're left with this very neat excess at the position of the sun, which we interpreted as a gamma ray signal from the sun. And this is at near 1 TeV, and it clearly has the profile of a source-like thing, and we're able to fit it with an extended disk of about 0.25 degrees exactly. And then we repeat this process at multiple bins and are able to extract a full gamma ray spectrum of the sun from Hawk. And this is what the TeV measurements look like. So on the left, you're seeing the Fermi measurements in GeV energies taken over almost 12 years. And this half is also similar to the plot that I showed you earlier. On the right is the Hawk measurements. So the red solid line is 6 years of Hawk spectrum from the sun. And the blue and the green lines is basically if I split the Hawk data into two halves, the blue is solar minimum and the green is solar maximum. So again, you can see the clear dependence on the solar cycle. The gamma ray flux from the sun is much higher during the solar minimum than the solar maximum. In fact, almost all of our signal is coming from the solar minimum. And we do observe the observed spectrum extends just above 3 TeV. So this paper is now up on arXiv, and you can read more details on it. It's currently under review by the journal. So this basically reflects the first solid measurements that were taken of the sun at very high energies. And you can clearly see that the spectrum is much softer than what it was at GeV energies. So what this is telling us is that there's actually finally a cutoff or a spectral break occurring at these energies. And this is perhaps a clue for people trying to model these phenomenon in the magnetic fields of the sun. So, but it still preserves this anti-correlation with the solar activity currently, which again remains a puzzle, and we cannot explain why this is so. So this is an exciting measurement, but there is, of course, a lot to look forward to. The dream would be to basically observe the sun with high sensitivity for at least another half a decade as it passes through the next solar cycle. Fortunately, we do have a couple of instruments on the horizon. One is what we call Hawk's Southern Hemisphere counterpart, or the Southern Wide Field Gamma Ray Observation, which is currently in the planning stage. And its projected sensitivity exceeds Hawk by an order of magnitude. And already within the last year, LASSO, this other much bigger version of Hawk in China, has become operational, and it is also taking data on the sun. So hopefully LASSO will be able to confirm Hawk observations, and that means there's more exciting results to look forward from that as well. So yes, in some summary, we have observed the TeV gamma ray emission from the sun at very high significance. The signal seems robust, and we've verified it by the way. I showed you observations of the sun. We repeated the entire analysis on the moon as well, and found no hints of any such gamma ray excess. So, that this was a cross check for us that, the emission was indeed unique to the sun. And the flux that we observe shows clear time dependence with the solar cycle. It's much higher in the solar minimum than in the solar maximum. And the measured spectrum is also much softer compared to the Fermi observation, and it likely points towards the fact that we're finally hitting a cutoff as far as the process of the cosmic rays mirroring in the photosphere is concerned. But of course, theoretical explanations of these observations are still missing. Like I said, the observed flux is much higher than what the theory predicted. This time dependence or modulation is also not explained. The shape of the spectrum is also not explained. And while we can't do morphology studies at TeV energies, there have been done detailed studies of the solar disk at GeV, and those also present a puzzle. And now, of course, the highest energy observation itself remains unexplained. So I will stop here and take any comments or questions that you have. Thank you.
Thank you so much. Do you have any questions from people in person? You know, while you see, oh yeah. Sorry, wait a second, the microphone.
I would think you would detect that maybe the resolution is the problem. A halo around the moon, cosmic rays coming from behind the moon that are coming through relatively shallow ramage on the, near the surface of the moon would be producing gamma rays for sure. Have you thought about models like that, or do you see any evidence of a corona around the moon?
Could you relay the question to me? Because I'm afraid I could not get the audio clearly.
So if the cosmic rays are, of course, isotropic, so those that are coming from the direction of the moon and impacting on the outer layers of the moon when we're observing the moon from the Earth with Hawk, you would expect a gamma ray halo or a ring that would be roughly the diameter of the moon. And so have you looked for something of that sort, or thought about simulating how bright it would be, which would be not that difficult to do?
So not at TeV energies, at least what we observe around the moons to be consistent with our isotropic background so far.
Okay. More questions from you? No, while you think, you showed the spectrum of Hawk in the in the minimum and maximum epochs about how many this one. So how many data points could you identify in the Hawk energy range? We see the curves, the spectral fields, but what are the observational points? How many do you have?
So because of how wide our energy resolution is, we're hesitant to give individual data points. That is why we specify the entire range of the spectrum. If I had to put a data point, it would have very wide X angular bars. So for now, the normalization of the spectrum is given here, and that's like about 10 to the minus 12, and it has an index of about 3.7.
So can we say that the blue curve of the solar minimum minimal energy point is this giving a genuine information that the Hawk data points are maybe a factor 2 or 3 only smaller than the maximum cosmic ray upper bound, or is it a genuine indication that the process is so efficient, the mirroring process is so efficient, or we should take this with cum grano salis?
So at this point, yes, the normalization is very well measured. So we can definitely say that it is a few factors. It's about 20% of the upper bound, at least in solar minimum. Yep. Okay,
that is impressively close, right, to the maximum.
Yes, so yes, it's a very high efficiency. Yes.
And it's almost everything is mirrored.
Yes.
Yeah. Okay. Any more questions from here? No. Let's see online. Don't be shy online. No. All right. Okay, let's thank both our speakers again. And see you next week. Thank you.